Okay, guys, in this video lesson, we're going to talk about power. Okay, it is the last video lesson of this unit, so here we go. Now, power, if you recall, is something that we've already studied. Remember, if we talked about power before, power is measured in watts, and it's a rate, right? It's a speed. Okay, so it's the speed, or it's the amount of joules of energy per second that we have in our system. Now, we've done power before. We're just going to apply that concept to circuits now, okay? So doing that, we want to be able to use power in reference to current, charge, and voltage. So what we got to do is get power somehow out of these two equations, okay? And if you take a look at that, well, current flow is a coulomb per second, right? That's coulombs of charge per time. And voltage, or our electric potential, is joules of energy per coulomb. So it's our energy content per coulomb. If you notice, we have coulombs in the numerator here. We have coulombs in the denominator here. So if we were to take our current and multiply it by our voltage, label-wise, the coulombs would cancel out, and we would get a joule per second. Okay, and that's what power is for us. So we can pretty simply find power in any circuit as long as we know the voltage drop across that circuit and we know the current flow inside the circuit, all right? Which means the watts that we have, for power, is equal to the amperage that is running times the volts, all right? These are two things that we actually can measure in a lab setting. Now, thinking about water models again, if we take a look at this idea, we know that the taller the waterfall, the higher the voltage, okay? That means as water falls over that thing, there's more height there, or there's more potential for the energy to transfer into our device that we're running. We've also talked about how the bigger the river, that means the more water that flows past a point in a given amount of time, that's our current, okay? So the same thing, applying these two concepts together, if you had, a short waterfall with no water in it versus a tall waterfall like Niagara Falls that's dumping billions of gallons of water through it, we're going to get a lot more power out of a tall waterfall that also has lots of water. Okay, a tall waterfall with a little bit of water, not much power there. Okay, a short waterfall with lots and lots of water could generate a similar amount of power as a taller one, depending on that flow of current. Right. So keep in mind that the work that we do here can be increased by either increasing the voltage or the current. Okay, so we have the ability to vary voltage in our circuitry or vary current in our circuitry by adjusting resistance that allows us to identify or generate the amount of power that we want to have. Okay. Now, here's two practice problems to make sure that we're comfortable with the math with our power. So go ahead and work through these, solve them, pause the video, and when you're done, unpause the video, and we'll do the answers. Okay, now let's solve it. So first one, we know the voltage in our normal household circuit. We know our amperage that we get. So our power we can get is 120 volts times 15 amps. Okay. Now this is a typical household circuit. So if we run 120 volts through a 15 amp circuit, we can provide 1,800 watts of power to any part of our house as we want to. Now keep in mind, if you have multiple things plugged into that circuit, each one of those things is going to take a certain amount of this power away. Okay. Now, let's take a look at that idea. If we have 60 watt light bulbs, all right, and we only have 1,800 watts to work with, in theory, if all the wattage went to just the light bulbs, we could figure out that we'd have 30 bulbs that we could power. So 1,800 watts divided by 60 is 30 bulbs. Now, in practice, an electrician will never wire up a house for 30 light bulbs all on the same 15 amp circuit. And the reason why, if you think about it, has nothing to do with the bulbs themselves, okay? It has to do with the wiring, okay? Because if you recall that there is resistance in the wire, there's resistance in the electrical boxes, there's resistance in everything. So some of your power, some of your energy goes to pushing those electrons down that electrical wire. So because of that, they'll never do that in terms of your current flow. They would reduce that pretty significantly to make sure that the resistance in the wire and the electrical boxes and other things that are there wouldn't cause you to overload your circuit and trip your breakers. Okay. All right, guys. Here's just a couple examples of different things. So here we have 120 volts. That's a 475 watt motor on this. You see here listing here. We have our frequency here. We have AC current on this one. Over here we have 100 to 240 volts. It can run 50 or 60 hertz, 3.5 to 1.5 amps. So whatever this is, it can run lots of different things. Down here, we have a refrigerator running at 60 hertz only. We need 110 volts, you know. So you're looking at these, all of the different things in your house or your shop or your garage, they're rated to a certain amount of volts, a certain amount of current flow, and a certain amount of power. Okay, and those things have to align for them to work properly. All right, guys, that is it. Thank you.